The objective of this video is to find the steady state response of a linear circuit to sinusoidal excitation. The word steady state implies that we are finding the response of the system a long time after switching on the supply. And the term linear circuit implies that the circuit considered obeys the superposition theorem and homogeneity. Superposition simply states that the net response caused by the sum of two or more excitations is equal to the sum of the responses that would have been caused by each excitation individually. And homogeneity just ensures that the input and output are of the same kind. Let's begin with a simple RC network driven by a sinusoidal voltage source Vi. And Vi is equal to capital Vi, its amplitude, times cos omega t for t greater than or equal to 0 and 0 for t less than 0. It just means that we are switching on the supply at time t is equal to 0. And the capacitor is assumed to hold 0 charges initially. Note that we could have equally taken the input to be Vi sin omega t, but a cosine function is just sine shifted by pi by 2 radians. And the reason for using a cosine function would be evident a bit later into the video. So let's begin. Typically, to analyze a circuit, we follow 4 things. 1. Set up a differential equation. 2. Find a homogeneous solution. 3. Find a particular solution. And finally, 4. The general solution, which is just a sum of homogeneous and particular solution. Step 1. Setting up the differential equation. There are 2 nodes. The one on the left is the input node, and the node voltage is just the source voltage Vi. And the one on the right is the output node, and the node voltage is just the voltage across the capacitor. So we are effectively finding the voltage across a capacitor to a sinusoidal excitation. Let's apply Kirchhoff's current law at the output node. The incoming current, which is the current through the resistor, given by the difference in node voltages Vi minus Vc divided by the resistance R. And that equals the outgoing current, which is the current through the capacitor, given by the derivative of the voltage across it with respect to time, scaled by the capacitance of the capacitor, C. Substituting the input cosine function and rearranging the equation a bit, we arrive at the differential equation for the RC network. We are done with the step 1. Let's move on to step 2. To find the homogeneous solution, make the excitation 0 and just directly integrate the equation. The homogeneous solution is equal to some constant A times e power minus t by RC. But note, the objective is to find a steady state solution, which means we are looking at the circuit after a long time. As the homogeneous solution is just a decaying exponential, it dies out. So it's 0. Moving on, step 3 was to find the particular solution. But before that, let's cheat a bit and look at the actual output in the scope. Here's the input signal on the left, a cosine function. And here's the output signal on the right, which is nothing but the voltage across the capacitor. Placing the signals one over the other, we can observe that the output is also a cosine function, but scaled by some factor A and shifted by some angle phi. Now we know how the output looks like. So let's just plug it into the differential equation to find the amplitude and phase shift, and then we are essentially done. If we differentiate and use trig identities and keep on grinding at it for some time, we'll definitely obtain the amplitude and phase. But let's accept it. It's an absolute nightmare. So is there no other way? Of course not. There are several other simpler ways, but one of the most ingenious techniques is to exploit the power of complex variables. Instead of driving the network with a cosine function, let's try to drive it with an imaginary complex input, Vi e power j omega t. Okay, I understand it sounds completely random, but here's why it's useful. Here's a complex input Vi e power j omega t represented as an arrow on the complex plane. As time increases, it rotates about the origin. According to Euler's formula, we know that e power j omega t can be written as cos omega t plus j sin omega t, namely the real and imaginary parts. But note that when we look at the real part, it's exactly our cosine input. So in essence, we are trying to carry out an inverse superposition argument. Here's a network. We excited it with Vi and obtained an output Vo. Now we are exciting the same network but with a complex input, which is made up of two components, real and imaginary, and the real part gives us the intended input. Since we are dealing with linear circuits, the superposition principle implies that the output is also made up of real and imaginary components, therefore taking its real part would give us the intended output. So let's go ahead and solve the differential equation with the imaginary input. To indicate the difference between the required output and the output of this equation, I've added a tilde over it. We know that a linear differential equation with an exponential drive produces an exponential output scaled by some factor, say Vc. So let's just plug it in. Differentiate. Now the exponentials cancel out neatly. Rearranging a bit, we obtain the expression for the amplitude Vc. Therefore, the almost solution Vc tilde is equal to 1 by 1 plus j omega Rc times the complex input. Writing the complex number in its polar form, that is in terms of amplitude and phase, we obtain this expression, where phi is the tan inverse of minus omega Rc. The powers of the same base add, so we have effectively written the output in its polar form. Remember, this is not the solution. Taking the real part of Vc tilde will give us the actual solution. And there it is, the solution to our original differential equation with the cosine input. I completely understand performing all this complex algebra sounded a bit complicated, but it's really not. We're essentially done with the problem when we found the complex amplitude Vc. When we multiply the complex amplitude, it rotates the input by some angle, which is the required phase shift, and scales the input by some factor, which is the required amplitude. So the complex amplitude is the key. It encodes the amplitude and phase information. So once we arrive at the complex amplitude, we are essentially done with the problem. Taking the real part isn't a big deal. Let's review what we have done till now. We had a circuit model, the RC network. We set up a differential equation for it. We introduced a sinusoidal drive, went through some trig nightmare to arrive at the output. Then we decided to bypass this trig nightmare by introducing a complex exponential drive, worked through some complex algebra, which was far easier in comparison with the trig, and finally took the real part to arrive at the same output. This was better, there's no doubt about it. But is there an easier way? Let's take a closer look at the complex magnitude Vc. Divide the numerator and denominator by the factor 1 by j omega c. If we write the factor 1 by j omega c as Zc, it looks exactly like a voltage divider circuit with a DC voltage source of Vi volts. And note, the node voltages of the circuit are represented as complex magnitudes. Something really interesting is happening here. Let's explore this a bit further. Let's begin with the capacitor. The voltage across and the current through is represented by complex numbers with magnitude Vc and Ic. The current through a capacitor is given by the rate of change of the voltage across it. Plugging in the complex numbers and getting rid of the exponentials, we arrive at an Ohm's law-ish relationship between current and voltage, but the resistance is replaced by some factor, let's name it impedance, whose value is given by 1 by j omega c. Let's carry out the same thing for an inductor. The voltage across an inductor is equal to the rate of change of current passing through it. Doing the same, plugging in the complex numbers, we arrived at a similar relation, but the impedance value is given by j omega times the inductance. Carrying on the same thing for the resistor, we find the impedance of a resistor is the resistance itself. Now let's try analyzing an RLC network excited by a sinusoid. Instead of going through the traditional 4 steps, we will find the equivalent impedance model for the circuit. That is, replace the capacitor, resistor and inductor with their impedance values and replace the AC source with a DC source of Vi volts and the current through as I. But remember, all the values are complex numbers. Now look at this circuit. The advantage now is that we can use all the network analysis tools that we use to solve resistive DC networks, like Ohm's law, Thevenin's theorem, Norton's theorem and so on. For example, if we were to find the current, is just the voltage divided by the total impedance. But always remember, this is not the final solution. We are yet to multiply e power j omega t and take the real part to obtain the true solution. But generally, we are so used to it, we just stop at finding the complex magnitude. Multiplying e power j omega t and taking the real part is taken for granted. So here's the final big picture. While analyzing networks with sinusoidal excitation for their steady-state responses, all we need to do is find the equivalent impedance model, solve it with our DC analysis tools, and finally take the real part. No differential equation, no trig nightmares, just simple network analysis. So the next time when you come across the term phasor diagram of a circuit or a transformer or anything, you have to understand that you're looking at a snapshot of rotating complex numbers whose real part represents the real waveforms. I have added a link to a course on steady-state analysis. I highly recommend you guys to check it out to practice what we learned in this video. Thank you and do consider subscribing.